then v equals, not negative x plus y, right? Whoa, sorry, minus y. Second equation didn't change. Now add down. Yeah, I'll just put negative u plus v. You could put v minus u. And then negative, I'm going to wind up switching it anyway, right? Negative 2y. And then scale by negative 2. So how about we go negative 1/2 times negative u plus v equals y. I don't like that negative out there. So we distribute it through. Or, you know what, I'm going to pull a negative out of these. It really doesn't matter at this point, right? I'm going to pull a negative out. Because for some reason, I don't like the negative 1/2 out front. So 1/2, negative came out. It's now u minus v and y. All right. That's kind of cool. I like that. That's using elimination. The other thing you could do is solve this one for x or y and then plug it into that one, but it takes much longer. Okay, let's do it. We have our equation for y, we have our equation for x, and now we're going to do our Jacobian determinant in there. And because these were linear transformations, right? They were linear. These are linear transformations. Those are linear. So we should get constants here. Let's see. Partial of x with respect to u. 1/2. Partial of y with respect to v. Yeah, we get a negative 1 here times 1/2, so negative 1/2. Minus partial x with respect to v. 1/2. Partial y with respect to u. 1/2. Yeah? So these two together are negative 1/4 minus these two together is 1/4 again. So minus 2/4. So minus 1/2, but then absolute value. So it's 1/2. So this becomes 1/2 the double integral over s of e to the u over v dA. Now what? Type 2. We got to set up the limits of integration. So more to do here. Let me get back to this. Okay, here's where we were. Okay, let me draw that region again. So if you're doing a change of variables and your transformations are linear, then your new integral is just scaled by a number, right? That's I already said that. But if it's nonlinear, that doesn't happen. It's going to be something more complicated. All right, our region. It was 1, 0, 2 what? 2. What was it? Was it 1, 0?
It was 1, 1. It was 1, 1.
1, oh, it was 1, 1. That's right. 1, 1, and then 2, 2. All right. So 1, 1, 2, 2. And then negative 1, 1, negative 1, 1, and negative 2, 2. Like that. There we go. This is u, this is v. That's important. So here I can see that my v's are between, this is type 2 region. My v's are between two constants, 1 and 2. It's 1 and 2. And now I need to be able to write, this line, right? I need to have that written as u as a function of v. But what is that line? It's u equals v, isn't it? Because it's like the identity. It's like y equals x. Has a slope of 1. You can just tell visually, right? Like up 1 over 1, and it goes through the origin. So this is u equals v. And then this one is like the same thing the other way, negative slope. U is negative v. And so what's my u between? Negative v and v. And now set it up, right? So now the order is not up to me. I have to do it in the order here because it's not a rectangle. So when I'm here, I'm now going to go, I'm ready for the final integral. It's going to be 1/2 integral from 1 to 2, integral from negative v to v, and then e to the u over v d u d v. And can you integrate this with respect to u? Yeah, because the v is a constant on the bottom, right? So you can just, yeah, you can just scale it. So I'm going to have the computer do it just to show we can do it. Like it's going to have no problem with it now. So if I change this to e to the, if I change this to e to the, wonder how it does with u over v. Oh, it doesn't even have the integral. Hold on. Clear that. Integral e to the u over v with respect to u. No problem. No problem at all. Where is it? Shit. Right there, right? Oh, shoot. Ah, screwed it up. Whatever. You saw it. So we got it, right? At this point, it can be done. I'm going to stop here because we could integrate this with respect to u. We could plug in v and negative v, and I believe that step you would need integration by parts on that next integral, and then from that you plug in your 1 and 2, and you're in business. All right. So I hope that addresses your question of like, well, where do you choose? Sometimes you just have to try and hope for the best, and in this case it worked. And your homework for this, I believe there's only just a few problems. Oops, why am I opening that? Yeah, just a few for you to look at. Yeah. Yeah. Do what you can. All right? Do what you can. All right, we are officially done with chapter 12. Yes?
Are you going to have change of variables on the exam?
I don't remember. I don't recall. I'm not sure how your exam is going to go. Let's see. Let's take a look at last semester's exam. When was it? Was it summer? Oh, there it is. Final exam. We're looking at last semester's final. Now, this is in no way an indication, like, what this is not exactly, you're asking, you know, could this be on the final? I don't remember if I had it on the final. It could be. It's a totally valid, fair game to be on the final. First question here was Lagrange. Triple integral over E. Haven't talked about this yet. 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 Haven't talked about that yet. And that was it. So of the final exam, you can see, right, of everything, there are 2 problems right now that you could do. Yeah. It gives you some idea of the density of chapter 13, right? Now, this problem here, problem 1 and 2, could easily be a change of variable problem instead of a triple integral or, something like that.
Gotcha, okay.
Yeah. Now, the review I had given them in this class, let me see what this review looked like. I think the review is a monster. It's 31 pages. It's just problems to look at. There's all sorts of problems, old exams, old reviews. This is a final from, oh no, that's something else. Oh, there, no, that's a changed order of integration. Nope, that's not. Chill out, dude. I'm looking for any of these that were change variables. I swear that I've asked it before. Yeah. Oh, I've done a final like this before, where I give 3 problems. Problem 1 has A, B, C, and they all have different difficulty levels. And so you can do like the A problem, the B problem, B song. I forget what the order was here, but like if you want to get an A on the test, then you need to do all the A problems. If you want to get a B, but I'm not going to do that to you. I'm just showing you what that was. Yeah, I've found that if I give you choices, you just get bogged down. You just like get lost. So I don't know if I've ever asked to change a variable problem in the past. But it hasn't been because I didn't want to. It's because there's too much other there's too much other stuff. So, all right.
Give us a simple linear one as an example.
Do y'all like these? I mean, we could do these by request. Why don't you do the homework on them first, and then we'll get back to it. I also think on the final, I can't remember exactly, but there are 8 problems here. No, man, I'm wondering, did I grade all 8? I don't remember if I graded all 8. Or if I took like their best 7 or something. I don't know. Maybe we shouldn't have looked at that. But maybe we should have, because now you understand, like chapter 13, this is it right here. Everything we've done has really just been leading us up to this chapter. So, I was telling my Cal 2 class today, like they're just starting sequences and series, right? So, like, okay, this is not the time to be tired. This is not the time to be exhausted. This is time to gotta find that third wind or whatever. Chapter 13. Here we are. Can you believe it? Made it. So y'all are just going to have to let me know if you start having issues with things, understanding things. I still don't think that it's the material that's hard. I think it's the amount of material that's hard. It's how much of it is. And then like knowing the difference between what we're talking about. So keeping everything sorted in your mind is the real challenge. All right, so we're going to talk, have a introduction to vector fields, which is something some of you have seen in the past. Maybe not, all right? I'm going to act like you haven't. Now, we all know what a vector is, right? We defined vectors already. We have 2-dimensional vectors, 3-dimensional vectors. We didn't really go beyond that. And we're going to stick in 2 and 3D here as well. A vector field, on the other hand, right, is a function, capital F with a vector on top of it, right? Capital F. And what it does is it takes an input. The input is a point. And then at that point, it assigns a vector to that point. So when you look at think of like a magnetic field for like magnets in North and South Pole, right? If you were to put a plane on top, or put an XY axis on top of this plane, then at every point the magnetic field is different, right? It's got a different strength and it's pulling in a certain direction. So at each XY, at each point XY, pick this one right here, at that XY, what I would do is I would take that XY, I would plug it into some function, some vector function, capital F, and what it's going to give me is a vector. And that 2-dimensional vector is this green vector right here, right? And then that's going to happen at every single point. So at every point in here, there's a vector. Now I can't draw that, because if I draw it, it's just going to look like a big mess, isn't it? Just vectors everywhere. So we don't want to draw all of them, but we'll draw some of them. So notice here this vector has a direction, right, and a length. So this direction, that length. This one, the direction is different, right? And the length is longer, which would imply that this magnetic field is stronger here in that direction, right? Because it's a longer vector. That's the basic idea of a vector field. At every point in the space, you have a function that assigns to it a vector for each point. Now, this is it's a very blurry, not very good topographical map. So this is a mountain, right, or like hills, and then at each elevation, you imagine drawing a line around. Like imagine walking around the mountain and maintaining the same elevation, and drawing a line around that or a curve around the mountain. Then looking at it from the top, and you would get this. So these are what we call the elevation lines, and so at every point, if I were to pick a point, like imagine again, this is like an XY plane. If I pick a point here and just kind of like put a ball down, that ball's going to want to roll somewhere, right? And so that vector could represent the direction, and then if it's real steep, it's going to go fast. If it's kind of flat, it's going to go slow, right? So at every point, you could have a vector that represents the gradient at that point. Just giving you examples. There's that same idea right there, right? That same idea. There's another picture of these like level curves on hills, and then all the different vectors all over the place. So again, if I put every point in and show you all of them, it's just going to look like black, right? It's going to black the whole thing out because there will be vectors everywhere. But that's a lot of them, so you can see them. All right, so here's an example of your first vector field where I'm actually defining the vector field for you. What it does is it takes in an x and a y, it takes in the x coordinate and y coordinate of the point you're at, and what it does is it spits out a vector that is the negative of the y coordinate, so your x component is the negative of that y value, and then the y component is the positive of the x. So what's the value of this vector function at 0, 0? The 0 vector. You should get 0, 0, which you can see right here. All right? That's the 0 vector. Now, what is the value of the vector field at, let's go to 2, 0. So right here at this point, right, what's the vector at that point? 0, 2. All right, let's see. There it is, right? There it is. There's the vector 0, 2. Now, when we say the vector 0, 2, that means the x component's 0, the y component's 2. So you could have drawn that vector here, couldn't you? Because vectors can move around. But it's associated with this point. So we move the tail of it to that point so that we can associate it with that point. All right? Yes?
Why are the y and x reversed?
I made up a vector field.
Okay.
Yeah, that's a completely made up vector field. It's just like, hey, let's try that, see what it looks like, right? Let's see. What happens if we change this? What happens if we do f of 2, 2? 2, 2. 2, 2. Negative 2, 2. So what does that vector look like? Negative 2, 2. So if you start at the origin, you go negative 2, 2. It would be that vector going from here to here, right? But it needs to be positioned so that the tail of it's at the point 2, 2. So let me move up to 2, 2. There it is. Okay? And I could keep doing this, right? Start drawing all these vectors. And if I put a couple of them in there, I start to get a feel for what's happening. Now, those are not drawn to scale. Okay? They're not drawn to scale. Obviously, at this point, I have a very long vector, right? What happens as I move closer to the origin? See what's happening to these vector lengths. They're getting smaller, right? Yeah. But they all seem to be following like this circular pattern, right? So this blue is kind of a representation of what's happening. You have this like counterclockwise rotational look to the field, And the further away you get from the origin, the longer the vectors get. And then you can have the computer put more of them in there. Same shit, just more of them, right? All right? All right, so there's your first example of a vector field. For every point in the space, you have a vectors assigned to it. All right, now I have the ability to type in whatever you want me to put in. So you want to make up a vector function? We can make one up. So we have two components we're going to put in, f of x, y. So who wants to give me the x component? Whatever you want.
Sine.
Sine of x, sine of y, sine of x plus y, sine of x.
Cosine of y.
And you want squared? You want to square it? Let's square it. Okay, and then what do you want here? Cosine of y times x. Sure, why not? They don't have to be exclusively just x's and just y's, or vice versa. You can mix them up. It can be anything you can really come up with. Now, I've never put this into the computer, so we'll see. We will see. Okay, sine of x squared. I have to type it in the way the computer wants it. They use slightly different notation. Okay. Got to do it again. Okay. Sine of x. What the fuck? Did it just die on me? I hadn't even started. Hold on. Okay, let me try this again. All right. Just make sure it's going to work. Yes. Okay, delete that. Wow. Okay. Whoa. Okay, so let's do this. Let's show this vector field. Let's move things around so it knows what's going on. Let's just do sine of y. Try that. Y, enable dynamic. Okay, I think I got it this time. Wow. It's never happened. I'm not sure what's going on. It's not the function you gave me. I can't even get the damn thing to work. So I'm going to do one more thing. One more thing, and then we quit. Copy. Just open a new notebook. Paste. I think it's because it's embedded in that other thing. And then it was cosine x times y. Okay. There you go. For some reason, because it's embedded in that other document, I'm cross-referencing like a variable is assigned two different things. There's probably something weird going on in there. The code by itself runs fine. There it is. Okay, so as you move around, let's see. Let's take our y value up to let's hold our y constant. If we hold our y constant and move left and right, let's see what happens. Just weird shit, right? There it is. It is what it is, right? It is what it is. There's an example of a vector field. It's hard. It's not as easy as like just a circle, right? Where, oh, it's circular, and as you move away, they get bigger. No, this is much more complicated. Okay, let's go back. All right, so just like you have a vector field in two-dimensional space, you can have a vector field in three-dimensional space. So you take on a point in three-dimensional space, x, y, z, and then you assign to it a vector where it has an x, a y, and a z component, right? And an example of that, this is a visualization of Earth's magnetic field. So you can imagine like at every point on Earth, there's some sort of magnetic, a vector that represents a direction and a length, right? So it's a little harder to visualize these because we're in three-dimensional space. But you can imagine that at every point there's some vector, right, pointing in some direction. And you can put more of them in there, but then it starts to get a little bit hard to see what's going on, right? But nonetheless, there they are. Here's a very famous and important vector field. And the first example where I'm actually explicitly giving you the formula for it. It is f of x, y, z equals negative x over, what is this? Square root of x squared plus y squared plus z squared. So if I were to take some point in three-dimensional space, here it is. It has an x-coordinate, a y-coordinate, and a z-coordinate, right? And I want to assign a vector to that. And the x component of that is just going to be the negative of the x-coordinate divided by magnitude, the distance from the origin to here. What's that distance? The square root of x squared plus y squared plus z squared. So this is just, what I'm doing is I'm taking this x-coordinate and I'm dividing it by the length of the vector, or the length from here to here. And I do that for both the x, the y, and the z. I'm just returning the x-coordinate, y-coordinate, z-coordinate, but negative, which means I'm changing the direction. Let me show this vector field to you. Ready? I'll show you first. Let me move the vector around. See if you can notice what's happening. No matter where I move this vector.
Gravitational.
Exactly. It's gravity. So what's happening here is that no matter where I move in this space, my vector points back towards the origins, like this creepy stalker that's just like watching the origin the whole time, right? No matter what, that vector is pointing back to the origin. Now, if I show you the whole field, there it is, right? Everything's pointing back. And it's constant. It's constant, meaning all those vectors have the same length because you're dividing it by its own length. And so that would be a constant gravitational force. Now, in reality, gravity is what? How is it related to distance? Inversely to the square of the distance. So this would not be true gravity, but you could use this to model like gravity on the surface of Earth, where we can assume everything's pretty much the same distance from the center. So that is your first example of a vector field in three-dimensional space, gravitational field, right? All right, we're going to move on. You have the basic idea, right? That if you're given either two-dimensional or three-dimensional space, we can define a vector function on that space where you assign to every point in the space some vector. Now, remember that if you're given a scalar function, right? So we're going back to earlier chapters, right? If I give you a scalar function of two variables, then we define this thing called the gradient of that scalar function as, remember that notation? Gradient of f. It was the partial of f with respect to x, partial of f with respect to y. Right? So we've heard of this thing called gradient before. And then also if we're given a scalar function of three variables, then we can define the gradient of that by taking the three partials, respectively, x, y, and z. And it creates a vector, right? So the gradient of these scalar functions creates vectors, right? Which means that the gradients could be looked at as vector functions. They take in some point and they return a vector. And so this is actually our first example of a vector field, and it's called the gradient vector field. So if I were to give you a surface here, okay, if I were to give you a surface, now when we look at that, we're like, okay, look, that is a surface, right? This surface lives in what space?
2D?
It lives, the surface lives, if we look at it, if we plot it, like graph it, it would live in three-dimensional space, right? Three-dimensional space, right? But we can define what's called the gradient of this. The gradient of this field is the two-dimensional vector, like this, right? And for us, that would be 2x, y, x squared minus 3y squared. That would be the gradient vector field. So we could define this to be our capital F of xy equals this 2xy x squared minus 3y squared. Okay, so we need to make sense out of this. All right, we need to make sense out of this. What we've done is we've started with some surface, right, that lives in three-dimensional space, right? And from this surface, we took the gradient, we found the gradient of this thing, and we are defining a vector field to be the gradient of that. The question is, what is this, right? We're calling it the gradient vector field, but what is it? Well, if we go and we look at, the domain of this on the ground, right? The domain down here is two-dimensional, right? You've got the x, you've got the y. This vector field is two-dimensional. So if I were to ask you to graph this vector field, you'd get little vectors all over the place, wouldn't you? Okay, those vectors live on the ground over here. But what they represent up on the surface is your gradient, your direction of the most rapid rate of change. So I'm going to show that to you visually. The important distinction I want you to make is that this surface lives in 3D. The gradient vector field, right, that you create is a vector field that lives down here in the domain in two-dimensional space. We answered the question, right? All they asked was for the gradient vector field. We answered it, but again, want to show you the visualization of this. What's that?
Could this be used for like topographical maps and stuff?
Absolutely. This is what, if you know what the surface looks like, you can get your gradient vector field easily to get all those little arrows to figure out. All right, so here it is. This is that surface that we were looking at right here. This is it right here. Okay, there's your surface. If we look at that from the top, and what we've done is we've come through and we've cut it with what we call level curves. So that surface is kind of like rippling through, and we just cut it, cut it, cut it, cut it. These are where those cuts would come through. And now, if we look at that gradient vector field, kind of like projected on there it is. There's the gradient vector field. So let's go back to this surface. And what